It's like slam on the
I would love to see
Good morning, everyone. We want to continue what we started learning about last week before the exam. So we started learning about screws, threads, power screws. And today I would like to go over that quickly, as well as start learning about bolted connections, bolted connection. Specifically, we want to learn about how to find, of course, after learning about all the definitions and standards of bolts and screws, we want to be able to calculate a bolt stiffness and a member stiffness in a bolted connection, because we need that to find the stresses and design factors for a bolted connection. We need the stiffnesses of the bolt and the member. I would just like to go briefly, because I know over what we've already done, because last week I think we got into the exam, and maybe some of you have started on the homework, some did not. I would like to refresh it. But speaking of homeworks, we want to complete homework number 9 this week, homework number 10 this coming week, and homework number 11 before Thanksgiving. Because when we come back from Thanksgiving, we want to have one homework left and then the exam. So we don't have much time, all right? If you are also doing any Thanksgiving planning for Thanksgiving week, we are not going to have an in-person class the week of Thanksgiving, okay? So we're not having an in-person class that week. All right. So we quickly, and I'm going to go over that quickly just to make sure you're all clear on it. We learned about threads definition, the pitch, the major diameter, the minor diameter, the pitch diameter, and the lead, where the lead for single threaded, the lead is the same as the pitch. If we have double threaded, for example, then the lead would be twice the pitch. So when you go one rotation, you're going to get an axial translation that is 2 times the pitch. We learned about the 2 different standards, the unified and the metric, and the coarse series, fine series, and extra fine series. We looked at a basic profile for the metric, and table 8.1 had the metric threads dimensions, and table 8.2 had the unified screw threads dimensions. We looked at the tensile area A sub T, tensor area A sub T, which is we're going to use again today when doing bolt stiffness. So that's the tensile area. We learned about power screws, and I hope you got to enjoy the couple of videos I had on the Canvas course page about the jack screw and how it works using bolt screws. If you have not done that yet, please make sure you go to module 11 and check it out. In power screws, we learned about square threads and Acme threads, square threads and Acme threads. We learned that we use the mechanical advantage or the wedge concept to raise or lower a force F by applying a torque. So when we started looking at mechanics of power screws, we started by calculating the force PR to raise or PL to lower the force, and we use the equilibrium equations to find PR and PL as function of the force F, the friction coefficient, the lead L, the diameter, the average diameter D. We can find PR and PL. We use PR and PL to find the torque needed to raise or to lower the force. And we looked at the self-locking condition, and we learned that if I have a force sitting on a power screw, it is going to be in a self-locking condition if the friction is greater than 10 lambda, greater than 10 lambda. Next, we look at the torque that is needed to raise a load should there be no friction, theoretical condition. So we looked at that T naught as FL divided by 2 pi, and we use that to calculate the efficiency of power screws. This lowercase e equal to T naught divided by TR. And T naught, that theoretical torque, of course, is always going to be smaller than the one with friction. So the efficiency is always going to be less than 1. Less than 1. Next, we looked at using Acme threads instead of square threads in power screws. And this basically would add a friction component, So the equation 8.1 would become equation 8.5 here, where we introduce this secant alpha component. In addition to that, many times when we are raising a load using a power screw, we are using a collar. And as we turn the power screw, there is additional friction component between the collar and the body or the part that we are trying to raise or lower. This friction component would contribute a torque that is equal to T sub C for collar, that is equal to the force multiplied by the collar friction coefficient F sub C multiplied by D sub C, which is the average diameter of the collar divided by 2. Okay. After doing that, we started looking at the stresses in a body of a power screw. Stresses in the body of a power screw. And when the body is supporting a force, that force is putting it in compression as an axial force. So we ended up getting a sigma equal to the force divided by the area. And for the area here, we used the minor diameter D sub R. So we have 4F divided by pi dr squared. But remember that this is a compressive axial stress. Compressive axial stress within the body of the power screw. Also within the body of the power screw, there is a torque that is applied. So there is an internal torque that is going to develop a torsional shear stress tau equal to 16T divided by pi d cubed. and we're still using the minor diameter. And to keep this in context, if we are looking at the body of a power screw, and of course I'm showing here the threads quite exaggerated, but if we look at the body of the power screw, again we said that this body is under this axial sigma that is equal to F over A equal to 4F divided by pi dr squared, and this is compression. And we also have the torsional shear stress, tau, that is equal to 16T over pi dr cubed. Now these stresses are within the body of the power screw. So the tau is really acting on the outside. And sigma, this compressive stress, is everywhere. So anywhere within the body of the power screw, we have sigma. We also have a bearing stress, but this bearing stress is applied on the thread itself. So this is sigma bearing. So I have a bearing stress, and this sigma uppercase B, to differentiate between the bending stress and the bearing stress, is equal to, of course, it is compressive, so it's minus F divided by pi dm nt p over 2. And later on, we say, well, NT is the number of engaged threads. But really, when we have multiple engaged threads, the first thread sees the majority of the force, and it sees about 38%. So we say, well, we can replace that and say that this sigma bearing is equal to, instead of using F, I'll put 0.38 F. So minus, and of course, if I rewrite this, move the 2 up. For the F, I'm going to put 0.38 F divided by pi dm, and I'm going to replace NT with 1. So I end up with a P here. So this is the compressive or the bearing stress that is negative. Excuse me? Of course. I simply replaced F with 0.38 F and substituted 1 for NT. Good. Next, we started looking at the bending stress. And the bending is occurring at the section, like imagine if this, if these threads were treated as cantilevers, and I have the force applied here, then I have a pull at the top. I have this tension at the top and compression at the bottom and zero in between. So we have this bending stress, sigma B. So I have this bending. Where sigma is equal to 6F divided by pi dr. And again, we have N, T, and P. But we said for the worst case scenario, for the first thread engaged, I can say that this sigma bending is 6. And instead of F, I'm going to put 0.38F divided by pi dr. And for NTU, I'm going to put a 1 times P. The thing that is important to note that this bearing is also acting on this point at the root, at the root right here. With the bending, we get a transverse shear stress, but that transverse shear stress maximum is right at the center. So right here where this green point is, I have a tau, another tau in green, and this tau, maybe I should say transverse shear, tau is equal to 3/2 V/A, which is equal to 3F divided by pi dr NT threaded engaged multiplied by P. Now this shear stress is what would cause the stripping of the threads. But where does it act? It acts at a different point. But it is 0 at the root of the thread. Okay. Now where am I taking all that? I want to look at the worst case scenario where failure is going to occur. And I would look at this as a critical point. And I'm going to represent the state of a stress at a point here using a stress block. So I'm going to take this root and try to express all the stresses acting on it. This is my X direction. This is my Y direction. And this is my Z direction. So along the Y, I have a sigma, which we call it axial here, along the axis of the screw. And this is this force here, or this stress rather, I'm sorry, which is equal to 4F divided by pi dr squared. So this is acting on the Y face. Okay. Now I have this torsional shear stress. Now, in which direction is this acting? Yes, it's acting on this point, but with the twist, this torsion is acting in this direction, perpendicular to the paper, which is going to be the Z direction, right? So it's acting in the Z direction. So when we're looking at the element, I have my Y face, I have my X face, and I have my Z face. And I said this is acting in the Z direction, and it's acting on the top, on the Y plane, right? So I get a shear force here. And this would be equal to 16 T divided by pi d r cubed. We also have this bending stress. And look at this bending stress. It is acting, it's an axial stress in the X direction, and it's in tension. So I get here on this X face, I get this sigma B, lowercase b for bending. Now, please remember that the bearing is on the thread, and it's a bearing stress. So we're not going to include that on the stress elements. How about the transverse shear? Should that be there? Where is the transverse shear stress acting? It's acting right here, right? It's in the Y direction on the X plane, correct? But it's right at the center of the thread, not at the root. And what I'm looking at here is this point. So this is the point that I'm drawing a stress element for. So this is why we ended up looking at these three stresses. And again, if I'm looking at this sigma YZ, I should also see a sigma ZY. Now, looking at this stress block, it is clear that the X face does not have any shear components, right? So this would be a principal stress, this bearing stress. And then I can plot a North circle for the Y, Z planes. So we can have, we have one principal stress here, and we can find the other two principal stresses by looking at the YZ direction. So just keep this in mind, and we're going to get back to it when we do the example. So do you all see where the stresses are coming from? So these are the three stresses on a stress element: the sigma X or the bending, the sigma Y or the axial, and the tau YZ torsional shear stress. If I want to evaluate failure, I can always calculate the von Mises stress and use the distortion energy failure theory, where N, the design factor, is equal to SY divided by sigma prime. So this is what we're going to do with the sigma prime. We can use it to find the design factor. We already covered that to find the largest stress, the first thread of a screw nut, we used 0.38 F and we substitute 1 for NT. This example one that I hope some of you already went over it is a nice put together of the concept we just went over. It starts, first part of it, after saying we're using a square thread power screw, it gives the measured diameter of 32 millimeter. It gives a pitch of 4 millimeter, but it is double threaded. Okay, so it has double threads. What does that mean? It means that the lead is not going to be equal to the pitch, but it's going to be equal to double the pitch. So the lead is going to be 8 millimeter and not 4. And this is used as a power screw. We are given the coefficient of friction between the threads and the collar friction. Both of them are 0.08. We are given a collar diameter of 40 millimeter and a force of 6.4 kilonewton. We are asked to find the thread depth, width, pitch diameter, and minor diameter, and the lead. So part A is about thread standards, and it requires understanding of the thread definitions. So given that the measured diameter is 32, I can look at the thread profile and say, well, the measured diameter is 32. So what would be the average diameter right here? Now looking at a square thread, the thread depth is P over 2. Is P over 2. So if I want to find the mid-range diameter, I would take half the P over 2 from each side. So basically, I subtract a P over 2. So the average diameter would be the diameter, the measure, minus P over 2. So I get 30 millimeter for the average diameter. The minor diameter, dr, would simply be equal to d minus P, and I get 28 millimeter. The lead is N times P. N for double thread would be 2. And P is the 4 millimeters, so I get 8 millimeters. Next, we want to find the torque required to raise the screw and also the torque required to lower the screw. So this is a direct application of equations 8.1 and 8.6. We substitute for the force, for the average diameter, for the coefficient of friction 0.08, for the average diameter of 30 millimeters, and for the collar diameter of 40 millimeters and the collar friction 0.08, and again the force is 6.4. We find the raising torque to be 26.18 Newton meter. Likewise for the lowering, but of course lowering would require less torque, so it is 9.77 Newton meter. We also want to find the efficiency. So the efficiency is equal to T naught divided by TR, and T naught is FL divided by 2 pi. F is the force, L is the lead, divided by 2 pi, divided by the raising torque. I get an efficiency of 0.311, right? Or 31% efficiency. Why is it 31%? Because of the friction. If I want to improve the friction, I lower the improve the efficiency, I lower the frictional coefficient. Next, we want to calculate the stresses at the root of the threads, as well as the bearing stress. So I start by looking at the stresses within the body of the screw itself. I have the tau and the sigma, compressive stress and torsional shear stress. Straight substitution into the equation, I get a tau of 6.107 megapascal, a sigma of minus 10.39. Next, we look at the bearing with one thread carrying 38% of the force. So we calculate a bearing stress and we find it's equal to minus 12.9 megapascal. And at the root of the thread, we also have this bending stress. And we find the bending stress to be 41.5 megapascal. I can take these numbers and look at finding the principal stresses as well as the von Mises stresses, right? So which numbers I'm going to take? Tau, sigma, and sigma b, right? So I write them here, the tau. This is the sigma bending, and this is sigma, I'm sorry, the other way around. This is sigma axial, and this is sigma bending, right? Any questions so far? All right. Now, these stresses can be substituted in equation 514 to find the von Mises stress. But also, we can calculate the principal stresses. And again, as I mentioned, clearly sigma x, there are no shear stresses on the x face. So sigma x must be a principal stress. So 41.5 is a principal stress. I can use my Mohr circle concept. So I have one principal stress that is 41.5. And then if I apply the principal stress equation, sigma 1, sigma 2 is equal to sigma, of course, in this time, I'm going to do it in the YZ direction. So I'm going to use sigma Y plus sigma Z over 2 plus or minus for 1 and 2, the square root of sigma Y minus sigma Z over 2 squared plus tau YZ squared. When I apply this equation, I'm going to find two additional principal stresses. And if I write them down, I'm going to get here a 2.79 and a minus 13.18. So clearly, I will start labeling these as sigma 1, this is sigma 2, and this is sigma 3, because sigma 1 is greater than sigma 2, greater than sigma 3. And I can use these stresses to plot a 3D Mohr circles. And remember, Mohr circles are plotted on the sigma tau plane. So what I'm going to do in the sigma tau plane, I'm going to show my principal stresses. So I'm going to show here is sigma 1. Here is sigma 2. And here is sigma 3. Now what? We're going to fit Mohr circle between sigma 1 and sigma 2. I'm going to fit another more circle between sigma 2 and sigma 3. And I'm going to fit a third more circle between sigma 3 and sigma 1. Now this is useful because not only I can use sigma 1, sigma 2, and sigma 3 to find my sigma prime, but I can also use my more circle expression to find my tau max. So my absolute maximum shear stress is going to be equal to sigma 1 minus sigma 3. That's the diameter of the red circle divided by 2, because it is this one here. So this is tau max. You all see it? So we can use sigma 1, sigma 2, and sigma 3 in equation 512 to find sigma prime. And of course, sigma prime calculated from equation 512 is the same as what we calculated from 514. Both of them are 48.7 megapascal. And tau max is calculated using sigma 1 minus sigma 3 over 2. We find tau max to be 27.3 megapascal. In table 8.4, we have safe bearing pressures for power screws. And please note that this depending on the material of the screw and the nut material. And we have a range for the safe power, the safe bearing pressure. Table 8.5 gives us coefficients of friction for threaded pairs. So depending again on the screw material and the nut material, we are given the coefficients of frictions. Likewise, in table 8.6, we have the thrust collar friction coefficients for a collar. And of course, it depending on whether you are running or starting. The starting friction coefficient is higher than the running friction coefficient. And the combination of the collar and the thread, the collar and the material of the body you're trying to lift. So if you have soft steel on cast iron, it's different than hard steel on cast iron, and so on. All right, this concludes power screws, and we want to move to learning about fasteners and bolted connections. So some fasteners have a tapered shank and other are non-tapered shanks. We have tapered shanks for wood screws, sheet metal screws, concrete screws, and dry wheel screws. So these are the self-threading screws. Non-tapered shanks are for we have cap screws, machine screws, hex bolts, studs, and eye bolts. These are typically non-tapered. The non-tapered thread fasteners are used to connect or join two or more components. And these are the ones we want to focus on for bolted connections. What's the difference between bolts and screws? Both of them are common type of fasteners. The main difference is a bolt is designed to pass through a hole in the mating member and be secured by tightening a nut, versus a screw is designed to be inserted through a hole in one member to be joined and threaded to in a threaded hole in the mating member, as you can see here in the picture. So this is a bolt, there is a nut. This is a screw. This is threaded. The hole in the mating member is threaded, so there is no need for a nut. So that's the main difference between a bolt and a screw. But as you're going to see, when we start learning about these bolted connections, the grip length for each of these connections is going to be different. Everything under the head of the bolt here, all the way through the nut, is within the grip. But when I look at a connection like this, the grip length does not extend all the way even through the end of my screw. Okay. In figure 8-9, we are looking at a hexagon head. And these are heavy duty and may have a washer face. There is a fillet under the head and a fillet at the start of the thread. And we get chamfers on both ends. There is a chamfer here and a chamfer there. Usually there is stress concentration at the fillet, the start of the thread, and the thread root fillet in the plane of the nut, as we discussed for power screws. The washers are used under a bolt head to prevent sharp edge biting into the head fillets. When we apply a clamping torque, we are basically stretching the bolt almost to its elastic limit. So this is the clamping force. A good bolt length would allow 1 or 2 threads beyond the tightened nut. So you want to see 1 or 2 threads beyond the tightened nut. By the way, the W here, the width of the hexagon head, is usually 1.5 times the diameter of the bolt itself. Typical cap screws heads are like a Philister head, a flat head, and a hexagonal socket head. So we have cap screw heads, and we also have machine screws. What's the difference? With these cap screw heads, the threads do not extend all the way to the head, unlike the machine screws. These are threaded all the way. I like this picture because it shows some of the important dimensions as well as definition for a hexagon head bolt, which is one of the most common for engineering application. So we see W is typically 1.5 times the nominal diameter. The bolt length L is measured from below the head to the end of the threads. And again, an ideal bolt length is 1 or 2 threads project from the nut after it is tightened. So this is the head, this is the thread end, this is the thread end chamfer, and we have the bolt length L that is made out of the threaded length L sub T, as well as the unthreaded length lowercase l sub d. So this is L sub T, and this is L sub D. And we're going to use all of these. And it can get a little bit confusing, so please pay attention to the notations that we are using here. The threaded length for the English system is usually twice the diameter plus either 1/4 of an inch or 1/2 an inch, depending on the length. In the metric system, it is twice the diameter plus either 6 millimeter, 12 millimeter, or 25 millimeters. Nuts. The typical specification for nuts are given in Appendix A31. Like we said, for power screws, there are the engaged threads. In nuts, the first 3 threads of nut carry the majority of the loads. Usually, there is localized plastic strain in the first thread. And this is why for critical application, we want to avoid reusing nuts. That's why even if the nut looks good, we want to replace it for critical applications. There are the regular nuts with the washer face, with a chamfer on both sides, and with and there are also the jam nuts that are thinner than the regular nuts. And usually they are used as a second nut, or for applications where we cannot use a regular nut, we use a thinner one. And this is a washer face jam nut, and this is here chamfer on both sides jam nut. Different nut shapes. The hex, the winged nuts, hex with a double chamfer, self-locking, and a castle head. Also, we may or may not use washers. And again, washers are used to provide a consistent bearing surface for the bolt head or the nut. I can use a washer with a nut and with a bolt head. And again, it protects the bolt head fillet from hole edge conditions. And it also helps lock the bolt head or the nut to prevent loosening. Typically, we use a bolt joint to resist an external tension load that is trying to separate 2 parts that are connected together, or shear forces, or a combination. So we're looking here at a bolted connection in tension. So there is an external tensile load that is trying to separate the 2 parts that are connected. When we design these bolted connections, we want to make sure that they are strong enough to resist this external tensile load, to make sure that the 2 parts that are connected always remain in a grip. Otherwise, we get a loose connection. Okay. So one of the things we look at is the grip length, and we use a lowercase l for a grip length. For a bolted connection using a bolt, the grip length includes everything that is in compression by the bolt. So it goes from underneath the head of the bolt all the way to the nut on the other end, including even the washers. So you see everything that is gray here is within the grip. And these are all in compression. How about the bolt itself? The bolt, when I tighten the nut, I'm really stretching it. So the bolt is in tension. We refer to this clamping force as the preload. As the preload, the pre-tension, or the bolt preload. So this is even before we apply this external load P. Here we are looking at a pressure head vessel, and the tension now is coming from the pressure within the vessel, because the pressure within the vessel is trying to push this cap. So it's trying to separate the 2 parts by the pressure that's coming from the inside. So again, you can still think of these as subject to an external tension, trying to separate the two parts together. So we have a hex head cap screw that is tapped in a tapped hole. So there is a hole here, and it's used to fasten the cylinder head to the cylinder body. Please note that we have an O-ring seal that is not affecting the stiffness of the members within the grip, but it's just a seal. And only a part of the threaded length of the bolt contributes to the effective grip when I'm using a screw. So my grip length would stop somewhere here. And right now we're going to see where this is going to stop. So if I'm looking here at a screw in a tapped hole, the effective grip length is this lowercase l. And please note that the screw stops here. So this is the total length. So this is the end of my screw, even though my threaded hole still goes all the way to the end of my second member. So the thickness of the first member is T1. The thickness of the second member is T2. The grip length is going to be equal to H, where H is T1 plus the thickness of the washer, plus either T2 over 2 or D over 2, depending if T2 is less than D or T2 is greater than D. So T2 is the thickness of the second member. Is that clear? So this is how I calculate the grip length for tapped holes. During the preload, the bolts is stretched and the members are compressed. When on top of that, there is an external load, this external load is trying to stretch the bolt further and uncompress the members that are in or within the grip. So really, if I want to look at what happens when a load is applied, I can model this connection, the bolts and the member, as two springs connected in parallel. So in order to see which part of the force is going to the member and which is going to the bolt, we need to find the stiffness of the bolt as well as the stiffness of the members. And this is what we want to accomplish before we leave today. So the bolt may be modeled as an axially loaded rod, even though it has a part that is unthreaded and a part that is threaded. And we want to focus on LD, the unthreaded, and the lowercase lt, because that's the part within the grip. So even though there is an uppercase LT, but we're going to be using lowercase lt because that's the part within the grip. So when I have two springs connected now in series, I have the threaded part and the unthreaded part. They are like one spring followed by another spring. So two springs in series. The stiffness of two springs in series may be found by 1 over K equal to 1 over K1 plus 1 over K2. Or if I solve for K, I get K equals to K1, K2 divided by K1 plus K2. Where we're going to use K1 for the threaded portion and K2 for the unthreaded portion. So for the threaded portion, I'm going to use the tensile area, AT. So it is AE over L for a rod, the stiffness. So E and divided by the tensile length. For the unthreaded portion, I have the nominal area, A sub D, multiplied by E divided by the unthreaded length LD. I substitute KT for K1 and KD for K2 in this equation. So we can find equation 817 is going to give us the stiffness of the bolt. Okay. I did put here two figures for using a bolt versus using a screw to show the difference between the grip length in using a bolt versus using a tapped hole. This becomes the grip length becomes this L. And this is L is equal to H plus T2 over 2 or D over 2, depending on T2 compared to D. Please remember that the length, the total length of a bolt for a figure A is equal to the grip length, or is greater than the grip length plus H. And for figure B is lowercase h plus 1.5 D. These equations will give us the threaded length outside of the grip, the total threaded length. That's why it's uppercase L sub T. So in order to find the stiffness, we want to calculate the lowercase ld, lowercase lt, AD, which is the nominal area, the tensile stress area from tables 8.1 or 8.2, and then substitute in this equation KB. I meant to include the two pictures so you can see the difference between the grip lengths in both types of connections. This is an example of a tension joint, and again, pressure vessel is also another example of a tension joint. Next, we want to look at the member stiffness, the parts that are compressed. So you see, when I apply this clamping force, I am compressing the members. And this compressive stress is distributed from the face of the bolt head and the nut. It can be modeled as a cone with a top cut off. We call this a frustum. And we use that frustum to find the stiffness within the members. So it is a cone with the head being cut, and this cone is hollow on the inside. And what we're going to do is we're going to take a differential slice of that cone and start finding how much it is going to displace to find the stiffness of the member. So I look at the displacement of that differential slice, delta, d delta. And we say, if you remember, when we have parts in compression, delta is equal to PL over EA. So the height here is dx. So I have P times dx divided by EA. Now the area of that ring is pi multiplied by the outer diameter squared minus the inner diameter squared. Now the outer diameter, if I know the angle alpha, which we're going to say 30 degrees is what we're going to use later on. So if I know the angle alpha and I know the distance x, we can find R naught, and Ri is the inner diameter. So it is the diameter of the hole for the bolt. So it's equal to the diameter over 2, d being the diameter of the bolt. Now we can simplify that further. And then in order to find, if I substitute the area here and integrate from 0 to t for any thickness t, we can find delta, as in equation D here, function of alpha, uppercase D, lowercase d, and t, and the modulus of elasticity E. If I want to find the stiffness for that part of the member that has a thickness T, I divide P by delta, because P is equal to K times delta. So K is equal to P divided by delta. So I get this equation 819. And this can be used for any diameter of the like we see, we have here the uppercase D. This is where we start. This uppercase D would be equal to 1.5 the smaller case d, right? Because it is gonna be the diameter of the head or the diameter of the washer, if I'm using a washer. And the washer diameter is 1.5 times the diameter of the bolt. So I have this uppercase d and lowercase d, and I have alpha and I have the thickness. If I substitute for alpha equal 30 degrees, the equation will be simplified to equation 820. But I'm going to have more than one member within the grip. So these are, again, like we have the bolt, they are like springs connected in series. So I can use 1 over Km for the members equal to 1 over K1 plus 1 over K2, 1 over K3, and so on. If all the members within the grip are made of the same material, I can combine that and come up with equation 821. And in 821, we replace the uppercase D with D washer. So this is the diameter of the washer used. If you're not using a washer, you will use the diameter of the head of the bolt. Even better than that, if we substitute for a DW, a standard washer face diameter of 1.5 D and alpha equal 30 degrees, we get one simple equation for the stiffness of the members that is within this red box here, equation 822, where the stiffness of the member is function of the modulus of elasticity, the diameter of the bolt, the grip length L, and that's it. So we can use this equation to find the stiffness of the member. Now, this equation and others were compared to that of a finite element model. And we found that, of course, none of them coincide, but they are within the range. There is even an exponential curve fit of a finite element result that can be used depending on the material used. And we can find these coefficients A and B and use this equation to find the stiffness of the member. I encourage you to please go over example 8.2 before you attempt to complete homework number 10. Okay? Enjoy the day off, and I'll see you all next week. Thank you.